Hello there, and welcome to the Dreamy Ocean Channel. Allow your body to settle now, finding a comfortable stillness. Feel the gentle weight of your limbs, unclench your jaw, and let your shoulders soften away from your ears. Take a slow, deep breath, and as you exhale, release any lingering tension, letting it melt into the quiet space around you, like sand dissolving into the tide. Now imagine yourself standing at the edge of a vast, tranquil ocean, just as twilight paints the sky. The air is cool and still, and the only sound is the rhythmic hush of waves breaking softly on a distant, unseen shore. Below the surface, an immense dark expanse stretches, holding ancient secrets within its silent depths, each one a whispered mystery, waiting to be acknowledged by a dreaming mind. For beneath those calm, shimmering waters, beyond the reach of our everyday instruments lie truths so profound, so unexpected, they challenge the very boundaries of our scientific understanding, and perhaps even our imagination. Allow your mind to drift now like a leaf upon a gentle current as we softly explore the unseen currents of knowledge that flow through our planet's greatest, most enigmatic ocean. Acknowledging the scientific enigma, beneath the gentle undulations of the surface where sunlight dances in fleeting patterns, lies a realm of unimaginable scale and profound silence, stretching across 361 million square kilometers of our planet's face. This colossal expanse of water, often perceived as a singular entity, is in truth a collection of vast, interconnected basins, each holding secrets within its abyssal embrace. We, as inhabitants of the sunlit world, tend to gaze upon its shimmering skin. Yet the true volume of the ocean, its three-dimensional immensity, remains largely beyond the grasp of our daily consciousness. It is a world vertically stacked layer upon shifting layer, each deeper stratum, becoming progressively more alien, more challenging, and ultimately more enigmatic to the curious mind. Our understanding of this submerged cosmos, despite centuries of maritime exploration and decades of advanced scientific inquiry, remains remarkably nascent. Consider this: if Earth were an apple, the deepest trenches of the ocean would represent only a tiny, almost imperceptible scratch upon its surface. Yet even that minute furrow plunges deeper than the highest mountains soar above sea level. The Mariana Trench, a crescent-shaped scar in the western Pacific, descends to nearly 11,000 meters a distance so profound that if Mount Everest were placed within its chasm, its peak would still be submerged by more than 2,000 meters of water. This sheer verticality, this immense column of fluid, exerts a pressure so staggering that it reshapes our very comprehension of physical limits. At those extreme depths, the weight of the overlying water presses down with an intensity that seems almost abstract to our surface-dwelling experience. For every 10 meters one descends, the pressure increases by approximately 1 atmosphere, or about 14.5 pounds per square inch. This means that at the bottom of the Mariana Trench, the pressure exceeds 1,000 atmospheres, a crushing force of over 8 tons per square inch. To visualize this, imagine the weight of 50 jumbo jets concentrated onto the surface area of a single human thumb. It is a pressure that would instantly flatten any unprotected terrestrial organism, collapsing air-filled cavities, compressing bone and reducing flesh to an indiscernible pulp. Yet life persists there, utterly transformed, adapted to this relentless squeeze with an elegance that defies our intuitive understanding. The darkness, too, is absolute, a perpetual midnight that descends just beyond the epipelagic zone where the last vestiges of sunlight are absorbed and scattered by the water molecules. Below about 200 meters, photosynthesis ceases, and the vibrant hues of the surface world are replaced by an eternal gloom, broken only by the ethereal flashes of bioluminescence or the brief, piercing beams of submersible lights. In this perpetual night, eyes have evolved in fascinating ways, some becoming enormous, gathering every stray photon, while others have atrophied, entirely replaced by sophisticated sensory organs, attuned to pressure changes, chemical gradients, and the faintest vibrations. The very concept of color as we know it becomes meaningless in this realm where blue light penetrates furthest, and reds and yellows are swallowed whole within the first few dozen meters. The logistical challenges of exploring these unseen depths are immense, demanding engineering feats that push the boundaries of materials, science, and robotics. Sending even a remotely operated vehicle, a sophisticated eye on a tether, into the abyssal plains requires miles of specialized cable capable of withstanding both the pressure and the corrosive saline environment while transmitting data across vast distances. Manning a manned submersible allowing human eyes to witness these alien landscapes involves crafting vessels of unparalleled strength and resilience, meticulously designed to maintain a fragile bubble of surface-like conditions against the overwhelming forces of the deep. Each expedition is a monumental undertaking, costly in resources, time, and human ingenuity, yielding precious fragments of delta from a world that remains overwhelmingly vast and largely unexamined. Indeed, scientists estimate that we have explored less than 5% of the ocean's floor in any detail, and even less of its water column. This figure, often quoted, carries a quiet weight of astonishment when one truly considers its implication. It means that 95% of the largest habitat on our planet remains largely a mystery, a blank canvas awaiting discovery. We possess more detailed maps of the surface of Mars, of the lunar topography, and even of Venus hidden beneath its perpetual clouds, than we do of the seafloor directly beneath our own ships. This disparity highlights a fundamental paradox. The deep ocean physically closest to us is in many ways more remote, more inaccessible than worlds orbiting hundreds of millions of kilometers away. This immense gap in our knowledge is not due to a lack of scientific curiosity, but rather to the formidable barriers erected by nature itself. The very properties that make the ocean so vital to our planet's climate and life support systems, its vastness, its density, its crushing pressures, its light-absorbing qualities, are precisely those that render it so difficult to probe. Each sample retrieved, each photograph captured, each sonic ping echoed across the abyssal plains represents a triumph over these natural constraints, a tiny pinprick of illumination in an otherwise boundless darkness. Yet with each new discovery, the scale of the unknown often seems to expand, revealing layers of complexity and unexpected phenomena that challenge existing paradigms and provoke new questions. For instance, the ocean floor is not a static, featureless plain. It is a dynamic landscape of colossal mountain ranges deeper than the Rockies, stretching for tens of thousands of kilometers. Of vast, flat, abyssal plains punctuated by volcanic seamounts rising abruptly from the darkness. Of hydrothermal vents spewing superheated mineral-rich fluids from the Earth's interior, sustaining entire ecosystems independent of sunlight. And of deep-sea trenches, the subduction zones where oceanic crust plunges back into the mantle, shaping the very geology of our planet. Each of these features, when explored, offers a glimpse into processes that operate on scales and timelines far removed from our human experience, hinting at geological and biological histories yet to be fully deciphered. The scientific enigma of the deep ocean, therefore, is not merely about what we haven't seen, but about what we have seen that defies easy explanation. It is about the data points that don't fit the models, the organisms that challenge evolutionary assumptions, the geological formations that seem to have no terrestrial analogue, and the acoustic signatures that emanate from sources unknown. These are the quiet anomalies, the subtle contradictions that accumulate in scientific journals and research databases, often discussed in hushed tones at conferences, yet rarely broadcast with the certainty of established fact. They represent the leading edge of discovery, the blurry boundary where consensus science gives way to tantalizing hypothesis, where the known world ends and the truly unknown begins its silent, profound reign. As we gently drift into these considerations, letting the enormity of the ocean's unseen depths wash over our minds, we begin to acknowledge the humility required when confronting such a grand, untamed wilderness. It is a recognition that our maps are incomplete, our instruments imperfect, and our understanding, though growing, is but a flickering candle in a cosmic dark. The ocean, in its deepest, most enigmatic reaches, holds not just water and rock, but a profound mirror to the limits of our current knowledge, inviting us to peer beyond the familiar and embrace the extraordinary possibilities that lie beneath the waves, awaiting patient, open minds. Unexplained geochronological signatures, the vast, dark volume of the ocean, a fluid tapestry woven over eons, holds within its very essence a profound timeline, a record of planetary history etched into the ceaseless movement of water molecules. Yet as scientists probe deeper, extracting core samples from the sea floor and analyzing the subtle chemical fingerprints within the water itself, they sometimes encounter echoes that resonate from a time far more ancient than current models comfortably allow. These are the unexplained geochronological signatures, whispers of primordial origins or processes that defy the neat linear narratives we have constructed for our planet's watery realm. Consider the isotopic ratios of hydrogen and oxygen, the fundamental building blocks of water. Water molecules, while seemingly identical, carry subtle variations in their atomic nuclei, tiny differences that act like indelible tags marking their journey through the Earth's systems. Deuterium, a heavier isotope of hydrogen, and oxygen-18, a heavier isotope of oxygen, exist in specific proportions, depending on the water source and its history of evaporation, condensation, and interaction with rock. These ratios are like a delicate genetic code, telling a story of origin, whether the water condensed from an ancient atmosphere, emerged from volcanic outgassing, or was trapped within the Earth's mantle for unimaginable stretches of time. In certain remarkably deep and isolated pockets of the ocean, particularly within the interstitial waters of ancient sedimentary layers, or within the fluid inclusions found in deep-sea basalts, scientists have encountered isotopic signatures that deviate significantly from the expected. The usual ratios of deuterium to hydrogen, for instance, might be subtly shifted, hinting at water that has remained undisturbed, perhaps even cut off from the global hydrological cycle for millions, if not billions of years. These are not merely variations due to local evaporation or mixing. Rather, they suggest a distinct provenance of water mass, whose journey began in an epoch so distant it predates the very formation of our modern ocean basins. Imagine a droplet of water trapped within a mineral lattice for eons, shielded from the churning currents and the slow, inexorable exchange with the atmosphere. When such a droplet is finally released and analyzed, its isotopic fingerprint might reveal a composition more akin to water believed to have been present during Earth's early tumultuous phases before the great oceans coalesced. Scientists theorize that some of this primordial water could still be slowly outgassing from the Earth's mantle, a deep reservoir of hydrogen and oxygen, locked within mineral structures gradually percolating upwards through fissures and vents. If this is true, then the detection of anomalous isotopic ratios in specific deep-sea environments could be a direct echo of our planet's earliest aqueous beginnings, a silent testament to water that has never seen the sunlit surface. Beyond the water itself, the very bedrock of the ocean floor, the vast basaltic plains that underlie the deep, also presents its own set of geochronological puzzles. The conventional understanding of oceanic crust involves a continuous process of formation at mid-ocean ridges, where molten rock wells up, solidifies, and then slowly spreads outwards, eventually subducting back into the mantle at deep-sea trenches. This process creates a predictable pattern. The oceanic crust generally becomes progressively older as one moves away from the spreading centers. This elegant model, supported by paleomagnetic stripes and radiometric dating, forms the cornerstone of plate tectonics. However scattered throughout the immense oceanic basins, there are tantalizing anomalies regions where the age of the crust, as determined by radiometric dating techniques, appears to be unexpectedly ancient for its location. One might encounter basalts or gabbros rocks, typically associated with oceanic crust, yielding ages that are hundreds of millions of years older than the surrounding seafloor, sometimes even approaching or exceeding the age of the oldest known continental crust. These findings are perplexing. How could such venerable rock formations exist in areas expected to be relatively young, continuously recycled by the relentless engine of plate tectonics? Scientists grapple with several hypotheses to explain these geochronological ghosts. One possibility involves the fragmentation and submergence of ancient continental crustal blocks, microcontinents that were once part of larger landmasses but have since been stretched, thinned, and drowned beneath the waves. While some such features like Zealandia are now largely accepted, the discovery of other smaller and more enigmatic ancient crustal fragments beneath seemingly typical oceanic crust continues to challenge the simplicity of our maps. The isotopic signatures within these rocks, particularly those of strontium, neodymium, and lead, often bear the distinct mark of continental rather than oceanic origins, further deepening the mystery. They whisper of land masses long lost, swallowed by the sea, their ancient foundations now forming silent submerged mountains or plateaus. Another, perhaps more provocative theory suggests that certain areas of oceanic crust might not be formed through the conventional mid-ocean ridge process at all, or that they represent remnants of an earlier, more complex phase of Earth's geological history. Could there be regions where crustal formation occurred under vastly different conditions, perhaps even involving processes that are no longer active on a global scale? The dating of serpentinized peridotites, rocks that form when mantle material interacts with seawater, sometimes yields unusually old ages, suggesting that some deep-seated water rock interactions have been occurring for durations far exceeding the typical lifespan of oceanic crust. These rocks, often found in fracture zones or at slow-spreading ridges, offer a glimpse into the mantle's chemistry and its ancient relationship with water, posing questions about the very mechanisms of crustal formation and alteration over geological time. Even the sediments themselves, the fine layers of detritus that slowly accumulate on the abyssal plains, can hold unexpected chronological clues. Core samples meticulously drilled from the seafloor provide a stratified record of Earth's past with deeper layers, generally corresponding to older times. Yet occasions arise where microfossils, tiny skeletal remains of ancient marine organisms, are found in sediment layers dated much older or younger than their known evolutionary range. Such findings could indicate the reworking of sediments where older material is eroded and redeposited. However, in some cases, the context suggests otherwise, hinting at the survival of species in isolated refugia or the existence of previously unknown evolutionary lineages that challenge our paleontological timelines. The presence of unusually well-preserved organic matter yielding carbon-14 dates that seem incongruous with their geological depth might also suggest localized conditions of extreme preservation or the interaction with ancient sequestered carbon reservoirs. These geochronological signatures, these subtle anomalies in isotopic ratios, radiometric dates, and fossil records are not easily dismissed. They represent data points that gently tug at the edges of our established scientific frameworks, inviting us to reconsider the completeness of our understanding. They are the quiet echoes from deep time resonating through the water and rock, reminding us that the ocean in its immense antiquity holds stories far more complex and perhaps more astonishing than we have yet dared to fully comprehend. As we let these thoughts settle like fine sediment upon the deep floor, we allow our minds to consider the possibility that the very water surrounding us carries memories from the dawn of our world, still whispering its ancient tales in the deepest, most undisturbed corners of our planet. Anomalies in deep-sea physics. The immense silent weight of the ocean pressing down with an unimaginable force sculpts not only the geology of the abyssal plains, but also subtly alters the very fabric of the water itself. While we understand the fundamental principles of hydrostatic pressure, observing its relentless increase with depth, certain phenomena within the deep sea present quiet paradoxes challenging the completeness of our physical models and hinting at subtle deviations from expected behavior. These are the anomalies in deep-sea physics where the familiar properties of water seem to bend, if only slightly, under the colossal embrace of the deep. Water in its everyday form is often described as incompressible, a fluid that resists reduction in volume. Yet this is a simplification. Under the crushing burden of thousands of atmospheres, water does compress, albeit minutely. At the bottom of the Mariana Trench, a given volume of water is about 5% denser than the same volume at the surface. This seemingly small change accumulates across the vast vertical expanse of the ocean, contributing to a colossal increase in the total mass of the water column. However, scientists have on occasion observed localized density variations that seem to defy precise prediction, even accounting for temperature and salinity. Imagine a subtle, almost imperceptible shift in the water's internal structure, a whisper of deviation from the calculated norm. These localized anomalies, often detected through highly sensitive gravimetric surveys or precise measurements of sound speed, suggest that factors beyond the simple trinity of pressure, temperature, and salinity might be at play, subtly influencing the packing and interaction of water molecules in specific enigmatic regions of the abyss. Consider the propagation of sound, the primary means by which we remotely sense the deep ocean. The speed of sound in water is a delicate function of temperature, salinity, and, crucially, pressure. As pressure increases with depth, it generally causes sound to travel faster, squeezing the water molecules closer together and allowing vibrations to transmit more rapidly. This forms the basis of phenomena like the SOFAR channel, a natural sound duct where sound waves can travel for thousands of kilometers. Yet deep-sea acoustic surveys have occasionally detected unexplained distortions, unexpected attenuations, or even anomalous reflections of sound waves that do not perfectly align with the meticulously calibrated models. It is as if the water in certain pockets possesses a slightly different acoustic character, a subtle resistance or resonance that alters the expected journey of sound. Could it be the presence of microbubbles of unknown gases stabilized under extreme pressure, subtly altering the medium's density. Or perhaps the presence of undiscovered particulate matter, so fine as to be invisible to conventional sensors, yet numerous enough to scatter sound in peculiar ways. These acoustic echoes, faint and enigmatic, suggest that the deepest waters might hold secrets about their own physical composition, subtly influencing the very way we listen to them. The viscosity of water, its resistance to flow, is another property subtly affected by pressure. At surface conditions, water flows with a familiar ease, but as pressure mounts, the internal friction between water molecules changes, impacting how fluids move and mix. While the general trend indicates a slight increase in viscosity with pressure at typical deep-sea temperatures, the precise behavior in extreme localized environments such as near hydrothermal vents or within deep-sea brine pools presents a more complex picture. Here, superheated, chemically rich fluids erupt from the seafloor, or hypersaline waters collect in depressions, creating environments of intense gradients in temperature, chemistry, and pressure. Scientists hypothesize that within these extreme interfaces, the viscosity of water might behave in unexpected ways, leading to unusual mixing patterns or the formation of stable layered fluid structures that persist longer than anticipated. This could in turn influence the transport of heat, dissolved gases and nutrients, creating microenvironments with unique physical dynamics that challenge our broader models of deep ocean circulation and chemical transport. Furthermore, the very dynamics of chemical reactions are profoundly influenced by immense pressure. In the deep sea, where pressures can reach thousands of times atmospheric levels, chemical reaction rates and equilibrium constants can shift dramatically. Molecules that are unstable at the surface might become surprisingly stable, while others might react in entirely novel ways. For example, the formation and dissolution of certain minerals, or the complex organic reactions underpinning deep-sea chemosynthetic ecosystems, are all occurring under conditions that are challenging to replicate accurately in a laboratory setting. Scientists have observed instances of unusually rapid mineral precipitation in certain deep-sea fracture zones, or the unexpected persistence of complex organic molecules in sediments, hinting at chemical pathways or preservation mechanisms that are still not fully understood. It is as if the pressure itself acts as a silent catalyst or inhibitor, subtly steering the dance of atoms and molecules into configurations and rhythms rarely seen in the sunlit world. Even the interaction of water with the solid earth beneath it presents a pressure paradox. The sheer weight of the overlying ocean, a colossal, pervasive force, presses down upon the oceanic crust. While this pressure is generally considered in geological models, the subtle interplay between the fluid pressure and the solid rock can have unexpected consequences. Consider the possibility that fluctuating deep ocean currents or seismic events might induce minute transient pressure changes on the seafloor. Could these subtle shifts amplified by the immense background pressure trigger microfractures in the crust, or influence the migration of fluids within the upper mantle in ways we have yet to fully quantify? Some geophysicists theorize that the omnipresent pressure of the deep ocean might play a more active, albeit subtle role in regulating certain aspects of submarine seismic activity, or the slow, inexorable flow of heat from the Earth's interior, creating a feedback loop between water and rock that is still largely unmapped. The biological adaptations of deep-sea life to these crushing pressures are in themselves a testament to the ocean's physical extremes. Piezophiles, or pressure-loving organisms, possess specialized proteins and cell membranes that remain functional and stable under pressures that would instantly denature or rupture the cells of surface-dwelling life. While much is understood about these adaptations, the precise molecular mechanisms that allow certain enzymes to maintain their intricate three-dimensional structures or cell membranes to retain their fluidity and integrity under such stress still contain elements of mystery. There are ongoing research questions about whether these adaptations rely solely on known biochemical principles, or if they hint at subtle yet profound alterations in the physical properties of water itself within the cellular environment, allowing for stability against what should be an overwhelming, destructive force. It is a biological paradox where life thrives under conditions that seem to defy the very physics of organic chemistry, suggesting a deeper, more intricate co-evolution with its extreme environment. As we allow these considerations to gently unfold, we begin to appreciate that the pressure of the deep sea is not merely a crushing force, but a silent, pervasive sculptor, subtly altering the fundamental physics of water, influencing its density, its acoustic properties, its viscosity, and its chemical reactivity. These subtle anomalies, these quiet deviations from the expected, are not failures of our understanding, but rather gentle invitations to look closer, to refine our models, and to acknowledge that the deep ocean in its immense silent embrace holds physical secrets that continue to challenge and expand the boundaries of our scientific inquiry. The paradox lies not in the pressure itself, but in the unexpected ways its relentless hand shapes the very essence of the watery world, whispering of physical principles yet to be fully charted. Beyond tectonic explanations, the great silent canvas of the deep ocean floor, stretching in its immense undulating contours beneath kilometers of water, is largely understood through the grand, elegant narrative of plate tectonics. We expect to find the sweeping curves of mid-ocean ridges where new crust is born, the profound abyssal plains, vast and relatively featureless, and the sharp descending slopes of subduction zones where ancient crust returns to the Earth's fiery heart. Yet, as our sonar pulses map the hidden landscapes with increasing resolution, and as remotely operated vehicles venture into ever more remote chasms, scientists occasionally encounter topographies and submerged structures that seem to whisper of origins beyond the familiar dance of tectonic plates, presenting quiet enigmas that gently challenge our established geological models. Consider the countless seamounts, those solitary mountains rising from the abyssal plains, remnants of ancient volcanic activity. While many align neatly with known hotspots or ridge systems, there are others scattered across the vast basins whose genesis remains less clear. Some exhibit an unusual symmetry, a conical perfection that seems almost too precise for the chaotic forces of submarine volcanism, their flanks rising with an uncanny regularity from the flat seafloor. Others possess surprisingly flat tops known as guyots, which are generally understood to be ancient volcanoes that were once at sea level eroded by wave action and then slowly subsided over millions of years. However, the sheer number of these guyots sometimes found at depths that imply multiple synchronous periods of extensive global subsidence, or in locations far from typical volcanic chains, can present a puzzle. Scientists theorize about the exact mechanisms and timing of their formation, pondering if certain clusters suggest a more complex interplay of crustal sagging and episodic volcanic pulses, or perhaps even hint at unusual erosional forces at depths we do not yet fully comprehend. The compositions of some of these isolated seamounts, when sampled, can also reveal unexpected geochemical signatures suggesting mantle plumes with unusual isotopic ratios, or interactions with crustal materials that are not easily explained by standard volcanic processes. They stand as silent, submerged monuments, each one a subtle question mark on the geological map. Then there are the submerged plateaus, and microcontinental fragments which, while sometimes explained by the stretching and thinning of continental crust, occasionally present characteristics that defy easy categorization. These vast, elevated blocks of crust, often hundreds of kilometers across, can exhibit magnetic anomalies or gravity signatures that are distinct from both typical oceanic and continental crust. Some geophysical surveys have revealed underlying structures that appear to be remarkably ancient, with seismic reflection profiles hinting at complex folded layers, more akin to continental shields than the relatively simple layering of oceanic basalt. Scientists hypothesize that these could be relics of long-lost landmasses, fragments torn from larger continents during ancient rifting events, or perhaps even failed rifts, where continental breakup began, but never fully completed, leaving behind submerged continental remnants far from modern shorelines. The challenge lies in unequivocally distinguishing these from highly altered, unusually thick oceanic crust, a task that often requires costly and deep drilling expeditions to retrieve direct rock samples. The isotopic fingerprints of these rocks, if they can be obtained, are crucial, as they can sometimes tell a story of an origin much older and chemically distinct from the young, fresh basalt extruded at mid-ocean ridges. These submerged landforms are like forgotten islands of geological history, their stories obscured by the immense weight of the overlying water and the relentless march of geological time. Beyond these large-scale features, the deep ocean floor also reveals intricate networks of channels and canyons that at times seem to defy our understanding of submarine erosional processes. While turbidity currents, massive underwater landslides of sediment-laden water, are known to carve impressive canyons, some observed channels exhibit morphologies that are more reminiscent of ancient fluvial systems' riverbeds than the typical V-shaped profiles of turbidite channels. These channels can extend for thousands of kilometers across abyssal plains, branching and meandering with a complexity that suggests prolonged, steady flow rather than episodic catastrophic events. Scientists ponder the immense volumes of water and sediment required to carve such features, and the precise conditions under which such sustained flows could have occurred at depths far below any plausible ancient sea level. Could theirs be traces of colossal paleo rivers that once flowed across exposed continental shelves during periods of extreme glacial maximums, when global sea levels were hundreds of meters lower, and their channels were then extended and deepened by subsequent submarine processes? Or do they hint at unknown deep ocean currents driven by forces we do not yet fully appreciate, capable of long-term significant erosion on a scale we are only beginning to grasp? These channels are like cryptic hieroglyphs etched into the seafloor, each curve and branch telling a story of powerful ancient currents that shape the deep in ways we are still struggling to interpret. Furthermore, remote sensing technologies, particularly high-resolution multi-beam sonar, have occasionally revealed patterns and geometries on the seafloor that seem unusually regular, almost too organized to be solely the product of random geological forces. These are not always grand towering structures, but sometimes subtle arrangements of ridges, depressions, or linear features that extend for many kilometers. One might observe rectangular grids or parallel lines that stretch with an uncanny straightness across vast distances, or circular formations that appear surprisingly symmetrical. While many such patterns can eventually be attributed to known geological phenomena, such as fault lines, sediment waves, or specific volcanic fissure eruptions, there remain instances where the regularity and scale of these features challenge conventional explanations. Scientists must then consider if these are unusual manifestations of known processes, perhaps under specific rare conditions, or if they hint at entirely different, unrecognized mechanisms shaping the ocean floor. The temptation to attribute such regularity to non-natural origins is strong for some, but rigorous scientific inquiry demands that all known geological and oceanographic processes be exhausted first. These geometrically intriguing features serve as quiet reminders that the ocean floor can sometimes present an aesthetic order that confounds our expectations, prompting us to look beyond the immediate and consider the subtle, intricate forces that can sculpt the deep in unexpected ways. The discovery of these anomalies, the unusually symmetrical seamounts, the ancient crustal fragments in unexpected locations, the river-like channels meandering across the abyss, and the geometrically regular seafloor patterns collectively underscores the profound extent of our uncharted knowledge. They are not merely isolated curiosities, but rather gentle, persistent nudges from the deep, inviting us to refine our understanding of Earth's geological history and the complex processes that shape its largest habitat. Each sonar ping that reveals an unexpected contour, each core sample that yields an anomalous rock adds another brushstroke to a map that is still largely blank, reminding us that the deep ocean in its silent, immense presence holds secrets of topography and structure that continue to challenge the neat boundaries of our current scientific explanations. As we allow these images of hidden mountains and ancient channels to drift through our minds, we acknowledge the endless possibilities that lie beneath the waves, waiting for the patient observer to truly comprehend their profound and enigmatic stories. Cryptic bioacoustic signatures. In the perpetual midnight of the abyssal plains where sunlight never penetrates and visual cues are scarce, sound becomes the dominant sense, a resonant tapestry woven through the vast, dark waters. Marine life, from the smallest snapping shrimp to the largest baleen whales, communicates, navigates, and hunts through a complex orchestra of clicks, whistles, moans, and thrums. Scientists, by deploying sensitive hydrophone arrays across the ocean basins, have been listening intently to this submerged symphony for decades, mapping the known voices of the deep. Yet amidst the familiar chorus, there are whispers, deep rumblings, and intricate patterns of sound that defy identification, emanating from sources unknown, creating cryptic bioacoustic signatures that resonate with profound mystery. These are not the easily recognizable calls of humpback whales singing their intricate, ever-evolving songs, nor the rapid-fire clicks of sperm whales echolocating for giant squid in the mesopelagic zone. Rather, these are sounds that possess an alien quality, a resonance or a structure that does not align with the known vocalizations of any identified marine creature or geological process. Imagine listening to a vast underwater radio, tuned to a frequency where familiar voices intermingle with strange resonant hums, percussive thumps, or complex undulating modulations that hint at a deliberate yet utterly foreign origin. One such category of enigmatic sounds comprises ultra-low frequency pulses, often detected across vast distances by hydrophone networks, originally designed to monitor seismic activity or detect clandestine submarine movements. These deep infrasonic vibrations below the range of human hearing are sometimes so powerful that they can be picked up by hydrophones thousands of kilometers apart, making precise source localization incredibly challenging. Scientists have recorded sustained rhythmic patterns of these low-frequency pulses, sometimes lasting for many minutes, even hours, exhibiting a regularity that suggests a living, breathing entity rather than random geological noise. The sheer energy required to generate such powerful low-frequency sounds points towards sources of immense size, prompting speculative whispers of undiscovered megafauna creatures of colossal proportions, moving through the deepest, least explored trenches and abyssal plains their very movements or vocalizations reverberating through the entire ocean basin. Then there are the sounds characterized by their unusual frequency sweeps or their complex, almost melodic modulations. The upsweep. For instance, a powerful season-dependent sound recorded for decades in the Pacific begins as a narrow band sound and rises in frequency over several seconds, reaching peaks that resonate across the ocean. While some researchers now believe it might be linked to volcanic activity in the Pacific, its exact source and the consistent, almost structured nature of its upsweep remain a subject of ongoing debate and fascination. Similarly, the whistle. Another regularly recorded sound possesses a distinct rising frequency pattern unlike any known whale call. Its consistent structure and powerful amplitude suggest a biological origin, but the identity of the creature responsible remains elusive, a ghost in the acoustic data. These sounds are like fragments of an unknown language spoken in the dark, hinting at complex communication or environmental sensing by organisms we have yet to encounter. Other recordings reveal sounds that are even more bizarre, defying easy classification. The train sound, for example, named for its resemblance to the distant chugging of a locomotive, consists of a series of low-frequency pulses that rise and fall in pitch, lasting for minutes at a time. Its consistent pattern and powerful presence in the acoustic record suggest a persistent, perhaps migratory source. Could it be a species of deep-diving whale with an entirely unique vocalization strategy, or a different form of life altogether? Adapting its sonic output to the extreme pressures and vast distances of the deep. The slowdown is another such mystery, a long drawn-out sound that descends in frequency reminiscent of a ship's engine winding down, yet recorded far from shipping lanes and exhibiting a spectral signature inconsistent with anthropogenic noise. These sounds challenge our assumptions about the diversity of marine bioacoustics, pushing the boundaries of what we believe possible for biological sound production in the ocean. The difficulty in identifying the sources of these cryptic bioacoustic signatures stems from several profound challenges. Firstly, the sheer vastness and three-dimensional complexity of the ocean make source localization incredibly difficult. Sound travels differently through varying depths, temperatures and salinities, creating intricate paths and refractions that complicate triangulation. A sound detected by widely spaced hydrophones might originate from a source thousands of meters below, or from a distant point horizontally, its precise trajectory, a tangled puzzle of acoustic physics. Secondly, our knowledge of deep-sea fauna, especially the larger, rarer, and more elusive species, remains astonishingly incomplete. The vast majority of deep-sea ecosystems are unexplored, and new species are discovered with every deep-sea expedition. It is entirely plausible scientists believe that creatures of substantial size and unique vocal capabilities exist in these unexplored realms, their sounds simply awaiting correlation with their physical forms. Moreover, the extreme conditions of the deep ocean might necessitate entirely different mechanisms of sound production and reception than those found in surface waters. Organisms living under immense pressure might utilize unique anatomical structures or biochemical processes to generate and perceive sound, leading to acoustic signatures that are fundamentally different from those of shallower dwelling species. The very properties of water under extreme pressure, as discussed previously, could also subtly alter the way sounds are generated and propagate, adding another layer of complexity to their interpretation. These sounds are not merely noise. They are structured, often repetitive, and sometimes carry significant energy, suggesting deliberate production for communication, navigation, or foraging. Scientists employ sophisticated algorithms and machine learning techniques to sift through petabytes of acoustic data, attempting to find patterns, classify unknown signals, and distinguish between biological, geological, and anthropogenic sources. They compare new recordings against existing databases of known marine sounds looking for matches, or more often, for the glaring absence of a match. The continuous monitoring of these hydrophone arrays generates an overwhelming stream of data, a constant influx of whispers from the abyss, many of which remain stubbornly unclassified, filed away as unknown biological or unidentified acoustic event. These unclassified sounds are the quiet frontier of ocean acoustic science, beckoning researchers to explore further, to listen more closely, and to push the boundaries of their understanding. As we allow these resonant, enigmatic sounds to echo in our minds, we are reminded that the ocean is not a silent, empty void, but a living, vocal entity constantly communicating in ways we are only just beginning to decipher. The cryptic bioacoustic signatures from the abyss are not just scientific curiosities. They are profound invitations to acknowledge the limits of our current knowledge, to consider the possibility of life forms and communication methods far beyond our present imagination. They are the deep, slow breaths of an unseen world, whispering its ancient secrets through the dark waters, inviting us to listen more deeply, and perhaps to dream of the colossal, unseen voices that still resonate in the deepest, most mysterious corners of our planet. Unclassifiable biota and metabolic mysteries. In the perpetual darkness of the deep, where the crushing weight of kilometers of water presses down with an unyielding embrace, life has evolved in forms so utterly alien, so profoundly adapted, that they often defy the very classifications we have meticulously constructed in the sunlit world. Beyond the familiar clicks and calls that echo through the abyssal depths lie the organisms themselves, creatures whose very existence and metabolic processes present profound mysteries, pushing the boundaries of our biological understanding and hinting at life beyond the known code. Our conventional biological frameworks, built upon the foundation of photosynthesis and a relatively narrow range of chemical reactions, often struggle to encompass the sheer ingenuity and diversity of deep-sea life. Consider the creatures that populate the hydrothermal vents, those volcanic fissures spewing superheated, mineral-rich fluids from the Earth's interior. Here, in perpetual darkness, entire ecosystems thrive not on sunlight, but on chemosynthesis, a process where microorganisms convert inorganic chemicals such as hydrogen, sulfide, methane, or elemental sulfur into organic matter. While the broad strokes of chemosynthesis are understood, scientists frequently encounter microbial communities, particularly archaea and bacteria, whose precise metabolic pathways remain enigmatic. Some appear to thrive on chemical gradients so subtle or utilize energy sources so unusual that their biochemical machinery operates beyond the well-charted territories of known cellular respiration. These are the dark metabolisms, tiny powerhouses converting the very chemistry of the Earth into life, often with efficiencies or waste products that are still being painstakingly deciphered. Then there are the organisms themselves, the macroscopic inhabitants of the abyss, whose morphologies and physiologies often present unclassifiable features. Each deep-sea expedition brings forth new species, many of which are so distinct, so uniquely adapted, that they necessitate the creation of entirely new genera, families, and sometimes even orders. Imagine a fish whose bones are so demineralized that it is largely gelatinous, allowing its body to withstand immense pressure without imploding, yet its internal organs function with perfect precision. Or a worm-like creature that completely lacks a mouthgut or anus, instead housing symbiotic bacteria within its tissues that perform all its nutritional needs, effectively turning the animal into a living bioreactor. These are not merely variations on a theme. They represent fundamental departures from the standard biological blueprints, challenging our assumptions about how complex life can be structured and sustained. Some of these unclassifiable biota exhibit sensory organs or appendages that seem to function in ways we can only speculate about. There are deep-sea fish with enormous tubular eyes permanently fixed upwards, designed to capture the faintest bioluminescent flicker from above, yet their visual processing capabilities in total darkness remain a subject of intense research. Other creatures possess elongated, highly sensitive tentacles or antennae covered in chemosensory receptors, allowing them to detect minute chemical traces in the vast, dark water, perhaps sensing distant food sources or the presence of mates across kilometers of ocean. But how do these sensory inputs translate into a coherent perception of their world? What constitutes a smell or a taste in a liquid medium under thousands of atmospheres of pressure? The very architecture of their nervous systems often reveals adaptations that suggest processing strategies far removed from our own, hinting at unknown ways of interacting with their extreme environment. The phenomenon of gigantism in the deep sea, where certain species grow to enormous sizes compared to their shallow water relatives, is well documented, seen in colossal squid giant isopods and massive amphipods. Yet the underlying metabolic drivers for this gigantism remain a mystery. Is it a response to colder temperatures leading to slower metabolisms and longer lifespans, allowing for continuous growth? Or is it an adaptation to food scarcity where a larger body size allows for more efficient foraging, or the ability to endure longer periods between meals? The energy budgets of these massive creatures living in an energy-poor environment are often perplexing, suggesting highly efficient nutrient uptake or metabolic rates that are exceptionally low, allowing them to conserve energy over vast stretches of time. Conversely, some deep-sea microbes exhibit surprisingly rapid metabolic rates, thriving and reproducing quickly in environments that seem to offer minimal energy input, challenging our understanding of biological efficiency under extreme conditions. Beyond the visible organisms, the microbial world of the deep ocean is an even greater frontier of unclassifiable life and metabolic mysteries. Deep within the sediments kilometers below the sea floor, scientists have discovered a vast, deep biosphere of bacteria and archaea that can survive for millions of years, living on incredibly low energy fluxes, their metabolisms operating at a pace almost imperceptible to our measurements. These zombie microbes exist in a state of suspended animation, dividing perhaps only once every 1,000 years, if at all their very survival, a testament to an extreme form of energy conservation. Their genetic material often shows high divergence from known surface life, suggesting ancient evolutionary lineages that have been isolated for eons, evolving independently in the Earth's crustal darkness. Their metabolic pathways, often involving the reduction of sulfate, the oxidation of iron, or the utilization of hydrogen produced from water-rock interactions, represent forms of life fundamentally detached from the sun's energy. Even more profoundly, scientists are beginning to explore the possibility of a shadow biosphere, hypothetical life forms that might exist on Earth, but utilize entirely different biochemical principles than the DNA-RNA protein system common to all known life. While this remains a highly speculative hypothesis, the extreme and isolated environments of the deep sea, particularly within the Earth's crust or in exotic brine pools, are often cited as potential refugia, where such alternative biochemistries could have evolved and persisted. Could there be organisms that utilize different amino acids or a different solvent than water, or even a different genetic polymer. The possibility, however remote, is a tantalizing one, reminding us that our definition of life itself might be too narrowly constrained by our own familiar biochemistry. The challenges in studying these unclassifiable biota and metabolic mysteries are immense, retrieving deep-sea organisms alive and intact, and then maintaining them under laboratory conditions that faithfully replicate their extreme habitats is a monumental task. The sudden change in pressure temperature and light can be lethal, making it difficult to observe their natural behaviors or to study their delicate metabolic processes. Genetic sequencing, while powerful, can only tell us about the potential functions encoded in their DNA. It does not always reveal the actual biochemical pathways or the complex interactions within their ecosystems. Therefore, many discoveries remain tantalizing fragments of data: a unique protein, an unusual lipid, a strange enzyme that hint at a biology far richer and more diverse than we currently comprehend. As we allow these thoughts of extraordinary life forms and their cryptic metabolisms to gently settle into our consciousness, we are reminded that the deep ocean is not merely a dark, empty void, but a vibrant, living laboratory of evolution, constantly pushing the boundaries of what is possible for life to achieve. It is a realm where the known codes of biology are often stretched, bent, or even broken, revealing a universe of biological ingenuity beneath the waves. The unclassifiable biota and their metabolic mysteries are silent, living questions, inviting us to look beyond the familiar and embrace the astonishing, diverse forms of existence that thrive in Earth's deepest, most enigmatic waters, waiting for us to truly understand their profound stories. Anomalous element, ratios, and isotopic shifts. The ocean in its immense, ceaseless churning is a colossal chemical laboratory, a vast aqueous solution where every element found on Earth finds its place dissolved and dispersed, interacting in countless subtle ways. For centuries, oceanographers have meticulously measured the concentrations of these elements, from the abundant salts that give the sea its characteristic taste to the vanishingly rare trace metals essential for life. Yet beneath the veneer of expected uniformity within the deep, silent reaches, scientists occasionally detect anomalous element ratios and isotopic shifts that whisper of hidden chemical processes of unknown sources and of interactions far more complex than our current models fully encompass. Consider the delicate balance of trace metals, those minute quantities of elements like iron, copper, zinc, and manganese, which despite their low concentrations play pivotal roles in marine biology and geochemistry. While their distribution is generally understood to be influenced by riverine input, atmospheric deposition, and hydrothermal venting, deep-sea expeditions have on occasion encountered localized enrichments or depletions that defy these conventional explanations. Imagine a plume of water hundreds of meters below the surface exhibiting unexpectedly high levels of, say, dissolved nickel, far from any known hydrothermal vent field or continental margin. Where does this excess metal originate? Is it leaching from an undiscovered type of seafloor rock? Or is there a cryptic biological process sequestering and releasing it in unusual ways? These subtle chemical signatures are like faint trails in the dark, hinting at unseen geological features or unknown biological pumps that silently manipulate the ocean's elemental inventory. Even the fundamental nutrient ratios, particularly those of nitrogen, phosphorus, and silicon, which govern the productivity of marine ecosystems, can present enigmatic deviations. The Redfield ratio, a widely accepted biogeochemical constant, describes the average atomic ratio of these elements in phytoplankton, suggesting a predictable balance in the upper ocean. However, in certain deep, isolated basins, or within the interstitial waters of ancient sediments, scientists have observed nutrient ratios that diverge significantly from this expected balance. A profound excess of phosphorus relative to nitrogen, for instance, might be detected in a deep water mass, suggesting either an unusual source of phosphorus or an unexpected sink for nitrogen that operates outside the well-understood microbial nitrogen cycle. These imbalances can persist over vast scales, hinting at deep-sea microbial communities with highly specialized metabolisms or the slow, inexorable release of nutrients from geological reservoirs that have been isolated for millennia, subtly altering the chemical landscape in ways we are only beginning to perceive. Beyond the mere quantity of elements, it is the subtle variations in their isotopic composition that offer an even more profound window into the ocean's hidden chemistry. Isotopes, as we have touched upon, are different forms of the same element, varying only in the number of neutrons in their nucleus. These tiny mass differences lead to subtle fractionations during physical, chemical, and biological processes, creating unique isotopic fingerprints that can trace an element's journey through time and space. Take, for instance, the isotopes of carbon, specifically carbon-13 and carbon-14. The ratio of carbon-13 to carbon-12 can distinguish between carbon derived from ancient geological sources like methane from deep-sea seeps and carbon recently fixed by photosynthesis. Scientists have detected anomalous carbon-13 signatures in dissolved organic carbon or in methane plumes, far from known gas hydrate deposits, suggesting the presence of ancient sequestered carbon reservoirs slowly leaking from the seafloor, or perhaps even unknown microbial pathways that utilize unusual carbon sources. Similarly, carbon-14, the radioactive isotope used for dating, has sometimes yielded surprisingly old ages for deep ocean water masses, or dissolved organic matter even in areas thought to be relatively well mixed. These findings can indicate extremely slow, deep ocean circulation in certain isolated pockets, or the interaction with profoundly ancient fossil carbon that has been locked away for hundreds of thousands, if not millions of years, slowly dissolving into the deep, dark waters. Nitrogen isotopes, particularly the ratio of nitrogen-15 to nitrogen-14, offer another powerful tracer. This ratio is delicately influenced by microbial processes such as nitrogen fixation, nitrification, and denitrification. In regions of the deep ocean, particularly in oxygen minimum zones or within anoxic sediments, scientists have observed extreme shifts in nitrogen-15 values that are difficult to reconcile with known microbial metabolisms. These anomalous isotopic fingerprints might suggest the dominance of previously unrecognized microbial consortia, performing novel forms of nitrogen cycling or operating under conditions of extreme energy limitation in ways that profoundly alter the isotopic signature of the nitrogen they process. It is as if the microbial world in its deep hidden corners is performing a silent, intricate chemical dance, with nitrogen leaving isotopic clues that challenge our comprehensive understanding of the global nitrogen cycle. Sulfur isotopes, specifically the ratio of sulfur-34 to sulfur-32, also tell a compelling story. This ratio is highly sensitive to the presence of sulfate-reducing bacteria and sulfide-oxidizing archaea, which thrive in environments where oxygen is scarce. In deep-sea hydrothermal systems, or within the deep sub-sea floor sediments, scientists have found sulfur isotopic compositions that are unexpectedly light or heavy, deviating from the expected range for seawater sulfate or typical hydrothermal fluids. These anomalies can point to deep-seated geological sources of sulfur, perhaps from the mantle or from ancient evaporate deposits interacting with the overlying water in complex ways. Or they might indicate cryptic microbial sulfur cycles where undiscovered microorganisms are fractionating sulfur isotopes in highly unusual patterns, hinting at entirely new pathways for energy generation within the Earth's crustal darkness. These sulfur signatures are like a chemical echo of ancient microbial life or of powerful geological forces silently shaping the deep. Even the isotopes of metals such as iron, copper, and zinc are increasingly being used to unravel the ocean's chemical enigmas. These heavier elements can undergo isotopic fractionation during biological uptake, mineral precipitation, or high-temperature reactions with hydrothermal fluids. Researchers have observed unusual isotopic ratios of iron in deep-sea plumes, far from known vent systems suggesting novel sources of iron or unexpected processes of ion cycling that are not yet fully understood. Similarly, anomalous copper or zinc isotopic signatures in deep-sea sediments could indicate the activity of unique metalloenzymes in deep-sea organisms, or the formation of mineral phases under extreme pressures and temperatures that preferentially incorporate certain isotopes. These metallic fingerprints, subtle and often challenging to measure, are like tiny, persistent whispers from the deep, hinting at a hidden realm of biogeochemical interactions that are still largely unmapped. Finally, the noble gases helium, neon, argon, krypton, and xenon, with their inert nature, serve as exceptional tracers. Relatively unaffected by chemical reactions, their isotopic ratios primarily reflecting their origin. Anomalous enrichments of helium-3, a primordial isotope typically associated with the Earth's mantle, have been detected in deep-sea plumes, far from known mid-ocean ridges or hotspots. These unexpected helium-3 spikes suggest the possibility of deeper unknown magmatic activity, or the slow, pervasive outgassing of mantle material through previously unrecognized conduits in the oceanic crust. Similarly, the isotopic ratios of neon and argon can sometimes indicate the presence of ancient atmospheric components trapped within fluid inclusions in deep-sea rocks, providing a direct glimpse into the composition of Earth's early atmosphere preserved in the silent depths. These noble gas signatures are like ancient breaths held within the Earth for eons, now slowly exhaling their profound story into the deep ocean. As we gently contemplate these anomalous element ratios and isotopic shifts, we begin to perceive the ocean not just as a vast body of water, but as a dynamic, chemically intricate system constantly being shaped by geological forces, microbial life, and the inexorable march of time. These chemical enigmas are not simply data points. They are profound invitations to look beyond the surface, to delve into the hidden chemistry of the deep, and to acknowledge that the silent, immense waters hold secrets of composition and transformation that continue to challenge, perplex, and ultimately expand the boundaries of our scientific understanding. They are the chemical whispers from the abyss, telling a silent, profound story of an ancient, ever-changing world, inviting us to listen more closely to its hidden chemical language. Unpredictable, global circulation, anomalies. The colossal engine of the global ocean, a vast, intricately woven system of currents and countercurrents, relentlessly shapes our planet's climate, distributes heat from the equator to the poles and cycles vital nutrients through its immense dark volume. We have, through decades of meticulous observation and sophisticated modeling, constructed a grand narrative of this global conveyor belt, understanding how dense cold water sinks in polar regions, slowly traversing the abyssal plains, only to eventually upwell and return to the sunlit surface. Yet even within this well-established framework, the deep ocean, with its immense scale and subtle complexities, presents tantalizing contradictions, revealing unpredictable anomalies in its global circulation that gently challenge the completeness of our understanding, hinting at unseen forces and unknown pathways. Consider the deep western boundary currents, those powerful narrow rivers of cold, dense water that cling to the western edges of ocean basins, silently transporting the weighty, newly formed bottom water from the icy reaches of the North Atlantic and the Antarctic towards the equator. These currents, like the North Atlantic deep water flowing south or the Antarctic bottom water, pushing north, are crucial arteries in the planet's circulatory system, carrying the breath of the surface world into the deepest trenches. Our models predict a relatively stable, predictable flow, a slow but inexorable movement. However, long-term monitoring efforts employing arrays of moored current meters and deep-diving floats have occasionally detected subtle yet significant deviations from this expected behavior. There have been instances of unexpected decelerations, prolonged periods of weakened flow, or even temporary localized reversals that do not neatly align with observed changes in surface winds or deep water formation rates. Imagine a colossal unseen hand subtly altering the course of an underwater river, slowing its momentum or nudging its path in ways that defy our immediate explanations. These anomalous shifts in the deep western boundary currents suggest that the deep ocean's response to external forcing or its internal dynamics might be far more nuanced and less synchronously predictable than our current large-scale models allow. Furthermore, the abyssal plains, those vast, seemingly featureless stretches of the deep sea floor, are often characterized in models as regions of slow, sluggish circulation, where water might reside for centuries before eventually upwelling. Yet, surprising observations have emerged from these quiet depths. Tracer studies utilizing inert chemical compounds like chlorofluorocarbons, CFCs, or specific noble gas isotopes introduced into the ocean by human activity have sometimes revealed unexpectedly rapid transport pathways, or more vigorous mixing in certain abyssal basins than previously thought. Imagine a faint, invisible dye injected into a supposedly stagnant pool, only to find it spreading with surprising speed, hinting at hidden conduits or unseen stirring mechanisms. These findings suggest that localized energetic processes, perhaps driven by subtle geothermal heating from the seafloor, or the interaction of deep currents with previously unmapped seamounts and ridges, might be generating more dynamic circulation patterns than our generalized models account for. The very stagnancy of the abyssal ocean. A foundational assumption occasionally gives way to these whispers of unseen motion, complicating our understanding of how efficiently the deep ocean sequesters carbon or distributes heat over geological timescales. The very process of bottom water formation, the genesis point of the deep ocean circulation, also harbors its own quiet contradictions. In the Labrador Sea, the Weddell Sea, and other key polar regions, intense cooling and brine rejection during sea ice formation create exceptionally cold, dense water that sinks to the sea floor, initiating the global conveyor. While the overall process is understood, the precise mechanisms that govern the rate and intensity of this sinking and the properties of the newly formed bottom water exhibit complex variability. Scientists have observed periods of anomalously weak convection, where the sinking process is less vigorous than expected, or sudden shifts in the temperature and salinity characteristics of the newly formed deep water, sometimes without clear atmospheric or cryospheric drivers. These unpredictable fluctuations in the heartbeat of the deep ocean suggest that localized feedback loops, perhaps involving intricate interactions between ocean eddies, sea ice dynamics, and the subtle stratification of the water column, are playing a more complex role than our broad-brush climate models fully incorporate. It is as if the Earth's deep ocean, in its most critical formation zones, possesses a subtle, unpredictable temperament capable of surprising shifts in its fundamental processes. Moving higher in the water column but still far from the sunlit surface, the mid-depth circulation also presents its share of enigmatic movements. Intermediate water masses such as the Antarctic. Intermediate water which forms in the Southern Ocean and spreads northward at depths of several hundred to 1,000 meters, or the Mediterranean outflow. Water, a dense saline plume that spills into the Atlantic, carry distinct temperature and salinity signatures. While their general pathways are known, observational data has sometimes revealed unexpected penetrations into remote basins or anomalous mixing rates with surrounding waters. Imagine a distinct layer of water like a silent, invisible river, suddenly veering off its expected course or dissolving into its surroundings with an unusual speed. These deviations challenge our parameterizations of turbulent mixing in the deep ocean, suggesting that the intricate interplay of internal waves, deep ocean tides, and the often rugged seafloor topography is generating localized turbulence and mixing at rates that are difficult to predict or incorporate into global models. The ocean's internal dynamics, its hidden turbulence, acts as a subtle, chaotic sculptor, subtly altering the expected journey of these intermediate water masses. Even the pervasive presence of mesoscale eddies, those swirling vortices of water that are ubiquitous throughout the ocean, can present anomalous behaviors in the deep. While eddies are a known part of ocean dynamics, transporting heat, salt, and nutrients, certain observations have revealed eddies of unusually large size, exceptional persistence, or unexpected energy propagating across vast ocean basins for months or even years. Some deep ocean eddies have been observed to detach from major current systems and then travel independently, creating localized, intense circulation cells that stir the deep waters in ways that are not easily predicted. These rogue eddies can interact with seamounts or ridges in complex ways, generating secondary currents or localized upwelling and downwelling that significantly perturb the ambient deep ocean flow. Such unpredictable energetic features challenge the simplified representations of eddy dynamics, often used in global climate models, suggesting that the deep ocean's internal weather system is far more complex and dynamic than we have yet fully mapped. The implications of these unpredictable global circulation anomalies are profound, rippling through our understanding of Earth's climate system and the very sustenance of deep-sea life. If the pathways and speeds of deep ocean currents are more variable or less predictable than assumed, it impacts our ability to forecast long-term climate trends, as the ocean plays a crucial role in absorbing and redistributing heat and carbon dioxide. Unexpected shifts in deep water upwelling or downwelling could alter the delivery of nutrients to surface ecosystems, or the ventilation of abyssal waters, impacting marine productivity and the health of deep-sea habitats. These anomalies are not merely academic curiosities. They are subtle indicators that the grand circulating heart of our planet holds secrets in its fluid dynamics. Secrets that continue to influence the planet in ways we are only beginning to grasp. As we allow these images of shifting currents and unexpected deep-sea motions to gently drift through our minds, we are reminded that the ocean, in its immense, silent presence, is a living, breathing system constantly in motion, yet often moving in ways that defy our neat categorizations. The currents of contradiction, the unpredictable global circulation anomalies, are not failures of our science, but rather gentle invitations to look closer, to listen more intently to the whispers of the deep, and to acknowledge that the fluid heart of our planet holds dynamic mysteries that continue to challenge, perplex, and ultimately expand the boundaries of our scientific inquiry. They are the deep, slow breaths of an unseen world, reminding us that its most profound movements are still unfolding in ways we are only just beginning to comprehend. Unidentified thermal and electromagnetic fluxes. The deep, silent ocean in its immense dark embrace is not merely a realm of crushing pressure and eternal night, but also a subtle stage for the invisible dance of energy. Beneath the kilometers of water far from the sun's warmth, the Earth's own internal furnace exhales its heat, and the planet's intricate magnetic field permeates every molecule. While we have meticulously mapped the broad flows of geothermal energy and charted the general contours of the geomagnetic field, scientists occasionally detect faint, elusive signals, unidentified thermal and electromagnetic fluxes that whisper of hidden energy sources and processes, operating beyond the comfortable boundaries of our current understanding, creating quiet enigmas in the very fabric of the deep. Consider first the subtle movements of heat within the abyssal realm. We understand that heat continuously flows from the Earth's molten core through the mantle and eventually escapes through the oceanic crust, often dramatically at hydrothermal vents, where superheated mineral-rich fluids erupt like geysers from the seafloor. Yet beyond these dramatic, well-charted oases, there are observations of more diffuse, less obvious thermal anomalies that gently challenge our models of heat transport. Imagine a vast, undulating plain of sediment stretching into the unseen distance, where sensitive temperature probes lowered with painstaking care detect a background heat flux that is consistently subtly higher than predicted for the age and thickness of the underlying crust. This is not the dramatic surge of a black smoker, but a pervasive, gentle warmth radiating from an unseen source, a silent breath from the Earth's interior. Scientists theorize that this could be due to undiscovered very low temperature, diffuse venting occurring over vast, unmapped areas of the seafloor, a slow, widespread seepage of warm fluids rather than concentrated eruptions. Or it could hint at unusual geological processes within the crust or uppermost mantle, perhaps deep-seated chemical reactions like serpentinization, where seawater interacts with mantle rock to generate heat over protracted periods, subtly warming the overlying water and sediments. The detection of these widespread anomalous thermal gradients, often difficult to localize precisely, suggests a more intricate, perhaps more active thermal landscape beneath the abyssal plains than our current models fully encompass. Furthermore, there have been tantalizing reports of transient thermal spikes in deep-sea environments, sudden localized increases in temperature detected by autonomous sensors, but without any corresponding seismic activity or known volcanic eruptions in the vicinity. Imagine a momentary, almost imperceptible blush of warmth, appearing and then fading in an otherwise stable, frigid environment. Could these fleeting thermal events be the result of small, deep-seated magma intrusions that penetrate the crust, but do not breach the seafloor, radiating heat outwards before solidifying? Or might they be linked to highly localized exothermic chemical reactions occurring within the sub-sea floor, perhaps involving the rapid breakdown of gas hydrates or the interaction of unusual fluid chemistries? Some researchers even ponder, albeit speculatively, if these could be related to unknown biological processes, perhaps colossal, undiscovered megafauna generating metabolic heat in their profound dark habitats, though this remains firmly in the realm of hypothesis. The challenge lies in distinguishing these genuine, anomalous thermal events from sensor malfunctions or the localized transient effects of deep-sea currents demanding highly robust and redundant measurement systems. These fleeting warmth signals are like silent flickers in the dark, hinting at an active, subtle thermal dynamism beneath the waves that defies easy explanation. Moving beyond heat, the deep ocean also plays host to invisible forces of electromagnetism, currents and fields that weave through the water and the underlying rock. While the Earth's main magnetic field is well characterized and we understand the influence of solar flares and geomagnetic storms, scientists have on occasion detected localized transient fluctuations in the magnetic field, strength or direction that cannot be neatly attributed to known geological structures, such as the magnetic anomalies imprinted in oceanic crust, or to external solar activity. Imagine a subtle, invisible tremor in the magnetic fabric of the deep, a momentary distortion of the Earth's great magnetic shield, far from any known source. These unexplained magnetic field variations, often measured by highly sensitive magnetometers deployed on the seafloor, could be related to unusual fluid flow within the crust or mantle, as the movement of electrically conductive seawater or molten rock can generate geoelectric effects. Or they might hint at undiscovered deep-sea mineral deposits with unique magnetic properties, or even more speculatively, to the piezomagnetism of rocks under immense fluctuating pressure, where mechanical stress generates a magnetic response. The electrical conductivity of the deep ocean, too, sometimes presents quiet anomalies. While the conductivity of seawater is well known to be influenced by its salinity and temperature, researchers have observed regions where the electrical conductivity of the water, or the underlying crust, deviates significantly from expected values without clear chemical or thermal drivers. Imagine a silent, invisible pathway in the deep where electricity flows with an unexpected ease or resistance. These anomalies could indicate unusual fluid migration pathways within the subsea floor, where highly saline brines or chemically distinct fluids create localized zones of enhanced conductivity. More provocatively, some scientists ponder if these could hint at the presence of unknown highly conductive materials within the deep crust, or even in the realm of extreme speculation, the interaction with exotic deep-seated plasma phenomena, perhaps within unique hydrothermal vent systems that generate highly ionized fluids. Even more enigmatic are the reports of transient electromagnetic pulses or sustained low-frequency electromagnetic signals detected in the deep ocean that cannot be readily explained by seismic activity, known biological processes or anthropogenic sources like submarines or cables. Imagine a brief, invisible flash of energy or a low, persistent hum resonating through the water felt only by highly specialized instruments. Could these be related to deep-sea tectonic stress release in unusual, non-seismic ways, where the immense pressures on the crust generate electromagnetic emissions? Or might they be linked to the piezoelectric effect in certain minerals, where mechanical stress generates an electrical charge potentially amplified by the colossal pressures of the deep? The detection of such signals is incredibly challenging, as the highly conductive seawater effectively shields and attenuates electromagnetic waves, making any detection a profound anomaly. These electromagnetic whispers, faint and fleeting, suggest that the deep ocean might be a stage for subtle, yet powerful electrical phenomena that we are only just beginning to perceive, perhaps even hinting at unknown forms of energy transfer or communication within its dark embrace. The intertwining of these thermal and electromagnetic anomalies is also a subject of intense scientific scrutiny. Are some of the unexplained thermal fluxes linked to the electromagnetic ones? For instance, could the movement of superheated fluids from deep within the Earth, creating thermal plumes, also generate measurable electrical currents as they interact with the surrounding conductive seawater and crustal rocks? The very processes that create heat, magma intrusions, serpentinization, or deep-seated chemical reactions can also involve the movement of charged particles or the alteration of magnetic minerals, potentially creating a complex, interconnected web of energy signatures. These linkages, if confirmed, would suggest a deeper, more integrated dynamism within the Earth's crust and mantle, subtly influencing the overlying ocean in ways that are currently beyond our comprehensive grasp. The technical challenges in detecting, localizing, and interpreting these deep-sea energy signatures are immense. It requires the deployment of highly sensitive, robust instrumentation, deep-sea thermistors, magnetometers, and electrical conductivity sensors capable of withstanding extreme pressures and operating autonomously for long periods in a corrosive environment. Filtering out the noise from known sources and distinguishing genuine anomalies from instrumental drift or environmental fluctuations demands sophisticated data processing and rigorous scientific validation. Each detected anomaly, each whisper of unidentified energy becomes a puzzle piece, inviting further investigation, deeper deployments, and more refined theoretical models to explain its enigmatic presence. As we allow these images of subtle warmth and invisible electromagnetic flickers to gently permeate our minds, we are reminded that the deep ocean is not a static, inert void, but a dynamic, energetic realm constantly exchanging forces and signals in ways we are only beginning to perceive. The unidentified thermal and electromagnetic fluxes are not merely scientific curiosities. They are profound invitations to look deeper, to listen more intently to the hidden energies of the abyss, and to acknowledge that the silent immense waters hold secrets of planetary power and subtle forces that continue to challenge, perplex, and ultimately expand the boundaries of our scientific inquiry. They are the deep, slow breaths of an unseen world, reminding us that its most profound energies are still unfolding in ways we are only just beginning to comprehend, waiting for us to truly understand their silent, powerful stories. Enigmatic formations and geometries. The deep, dark canvas of the ocean floor stretching in its immense, silent expanse is generally expected to display the grand, sweeping brushstrokes of geological forces, the linear scars of tectonic rifts, the undulating curves of abyssal hills, and the chaotic tumble of submarine landslides. Our scientific instruments piercing the watery veil with sound and light have meticulously charted vast regions, building a mosaic of mountains, valleys, and plains shaped by the slow, inexorable march of plate tectonics and the relentless sculpting of currents. Yet amidst these familiar geological narratives, scientists occasionally encounter formations and geometries that seem to possess an uncanny order patterns without precedent that defy easy explanation, hinting at processes or origins far more enigmatic than our current understanding comfortably allows. Imagine a vast, flat expanse of the abyssal plain, kilometers beneath the surface where the sediment lies undisturbed for millennia. A high-resolution multi-beam sonar system sweeping its acoustic gaze across this silent landscape might suddenly reveal an arrangement of ridges and depressions that align with an almost unsettling precision. These are not the random undulating patterns of sediment waves sculpted by currents, nor the jagged, irregular outlines of volcanic fissures. Instead, one might discern long, remarkably straight lines, extending for tens or even hundreds of kilometers, intersecting at seemingly deliberate angles, forming grids or rectilinear patterns that appear too organized, too symmetrical, to be solely the product of chance geological processes. Scientists grapple with the profound challenge of explaining such regularity. Could these be the subtle surface expressions of deeply buried ancient fault systems, whose linear weaknesses guide the slow compaction and erosion of overlying sediments in an unexpectedly precise manner? Or perhaps they are the ghost imprints of colossal, now vanished icebergs grounding on the seafloor. During ancient glacial periods, their immense flat bases carving perfectly straight furrows as they drifted. The sheer scale and geometric exactitude of some of these linear features often strains such explanations, leading to quiet contemplation about unknown forces at play in the deep. Beyond these vast linear arrays, there are also reports of surprisingly perfect circular or arc-shaped formations etched into the deep seafloor. These are not the familiar, often irregular craters left by meteorite impacts or the gradual organic curves of submarine volcanoes. Rather, they appear as almost perfectly drawn circles of uniform depth or elevation, sometimes many kilometers in diameter, standing in stark contrast to the surrounding chaotic topography. How could such precise, symmetrical structures arise from the turbulent, often violent geological processes of the deep one? Hypothesis suggests the slow, localized upwelling of fluids or gases from deep within the crust, creating a circular zone of altered sediment or mineral precipitation that gradually forms a topographic ring. Another might consider the unique dynamics of deep-sea currents, perhaps a persistent rotating eddy, powerful enough to scour the seafloor in a perfectly circular motion over geological timescales, although the stability and duration required for such an event would be exceptional. The precise, almost manufactured appearance of these circular features, however, often leaves researchers with a lingering sense of profound mystery, prompting questions about the limits of natural forces in creating such aesthetic order. Then there are the individual structures formations that rise from the seafloor with an architectural precision that seems to defy their natural origin. One might encounter solitary pillars standing vertically for hundreds of meters, their flanks surprisingly smooth and their summits flat, almost like colossal submerged monuments. While some columnar jointing can occur in volcanic rocks, creating hexagonal pillars, the scale and isolated nature of some deep-sea pillars often extend beyond these known geological phenomena. How could such immense solitary columns form without the surrounding material collapsing or eroding away in a less symmetrical fashion? Scientists might theorize about unique mineral precipitation around a central core, or the selective erosion of softer surrounding rock, leaving behind a harder, more resistant column. Yet the sheer regularity and often isolated grandeur of these formations often lead to a quiet sense of wonder, challenging the very definition of natural in the deep. Similarly, there are reports of vast, seemingly constructed walls or ramparts extending for many kilometers across the abyssal plains. These are not the chaotic, jumbled blocks of a landslide, nor the irregular steps of fault scarps. Instead, they present as relatively uniform, often vertically faced structures rising abruptly from the surrounding sediments, their crests remarkably level, their alignments strikingly linear. While some such features could be explained by the exposure of ancient, highly resistant rock layers through erosion or the uplifted edges of tectonic blocks, the consistent height and astonishing linearity of certain deep-sea walls can present a profound puzzle. Could these be the result of a very specific, prolonged interaction between deep ocean currents and unusual sediment types slowly sculpting these monumental barriers over eons? Or do they represent the remnants of ancient submerged geological events whose scale and precision are simply beyond our current interpretive models? These silent, submerged walls, standing as they do in the perpetual darkness, evoke a sense of immense, deliberate construction, a silent testament to forces we are only beginning to fathom. Even at the microscale, within the intricate ecosystems of hydrothermal vents or cold seeps, scientists occasionally discover mineral formations or biological constructions that exhibit patterns without precedent. Imagine delicate spiraling mineral structures growing from the vent chimneys with a mathematical precision that seems almost biologically engineered, yet composed entirely of inorganic sulfides and sulfates. Or fields of deep-sea sponges, anemones or tube worms, not growing in random clusters, but arranged in surprisingly regular, almost geometric arrays, their distributions seeming to follow an unseen organizing principle. While biological self-organization can lead to intricate patterns, the scale and exactitude of some of these formations can suggest an interaction with environmental factors, subtle chemical gradients, fluid flows, or pressure fluctuations that are far more nuanced and structured than our current understanding of deep-sea ecology encompasses. These smaller yet equally enigmatic patterns remind us that the deep ocean's capacity for order, whether geological or biological, extends across all scales, often in surprising and unexplained ways. The challenge in interpreting these enigmatic formations and geometries lies in several factors. Firstly, the remote nature of the deep ocean means that direct observation is rare and costly. Most data comes from acoustic surveys which provide shape and depth, but lack the detailed visual and compositional information needed for definitive geological identification. Secondly, the immense pressures and unique chemical environments of the deep can lead to geological processes and mineral formations that have no direct analog on the surface, making comparative analysis difficult. What might seem an impossible formation on land could, under deep-sea conditions, be an extreme but natural outcome of forces we do not yet fully understand. Finally, the vast timescales involved in deep ocean geology mean that features observed today could be the cumulative result of processes that operated over millions of years, under conditions that might have been vastly different from the present. These patterns without precedent, these geometrically precise formations and enigmatic structures, are not merely curiosities on the map of the deep. They are profound invitations to reconsider the elegance and complexity of Earth's geological and oceanographic processes. They are the silent, structured questions etched into the sea floor, whispering of unseen forces, unknown mechanisms, and perhaps even a deeper, more intricate order within the planet's largest habitat. As we allow these images of perfectly straight lines, precise circles, and silent towering walls to gently drift through our minds, we acknowledge the endless possibilities that lie beneath the waves, waiting for the patient observer to truly comprehend their profound and enigmatic stories, reminding us that the deep ocean, in its immense, silent presence, holds secrets of form and structure that continue to challenge the neat boundaries of our current scientific explanations. Interpreting the unexplainable in modern oceanography. In the quiet, ceaseless quest to understand the deep ocean, our human ingenuity has woven a complex web of sensors, instruments, and observational platforms, casting an ever-widening net across the vast, dark waters. From the silent, autonomous gliders that trace intricate paths through the water column, to the remotely operated vehicles that beam back fleeting images from abyssal trenches, and the vast networks of hydrophones that listen to the ocean's every whisper. We are now collecting data at an unprecedented scale, creating a veritable data deluge. This overwhelming torrent of information, while offering unparalleled insights, also brings with it a profound challenge: how to interpret the unexplainable, the anomalies, the faint signals that stubbornly refuse to fit into our meticulously constructed scientific models, creating quiet enigmas within the very heart of modern oceanography. Imagine the sheer volume of this incoming tide of information. Satellite altimeters orbiting hundreds of kilometers above the surface map, the subtle undulations of sea level with millimeter precision, revealing the great ocean currents and the swirling dance of mesoscale eddies. Deep-sea observatories permanently anchored to the seafloor continuously stream data on temperature, salinity pressure, and seismic activity year after year, accumulating petabytes of raw measurements. Acoustic arrays record the ceaseless symphony of the deep, capturing every click, hum, and rumble from countless marine creatures and geological processes. Multi-beam sonar systems mounted on research vessels paint intricate three-dimensional maps of the seafloor, revealing every seamount canyon and abyssal plain with astonishing detail. Each of these streams of data, immense in itself, is then combined, correlated, and analyzed, creating a picture of the ocean that is both breathtakingly comprehensive and overwhelmingly complex. The first challenge in this data deluge is simply its scale. Processing, storing, and analyzing such colossal datasets requires computational power and algorithmic sophistication that were unimaginable just a few decades ago. Scientists employ supercomputers, artificial intelligence, and machine learning algorithms to sift through the noise, to identify patterns, and to extract meaningful signals from the vast expanse of raw numbers. Yet even with these advanced tools, the sheer volume can obscure the subtle, the unusual, the truly anomalous. A faint, unexplained electromagnetic pulse, for instance, might be buried within terabytes of routine, geomagnetic data easily dismissed as instrumental noise or a transient environmental fluctuation, unless a finely tuned algorithm or a particularly astute human eye is specifically looking for such a deviation. The haystack of known information is so vast that finding the needle of the unknown becomes an exercise in profound patience and meticulous attention. Then comes the critical task of distinguishing signal from noise, the genuine anomaly from the mundane error. Deep-sea sensors operating under extreme conditions of pressure, cold and corrosive salinity, are susceptible to a myriad of malfunctions, biofouling by marine organisms, cable breaks, power fluctuations, or simple calibration drift. An unexpected spike in temperature might be a genuine thermal vent, or it could be a faulty thermistor. An unusual acoustic signature might be a new species vocalizing, or it could be the creaking of a submersible's hull, or the distant clang of a passing ship. Rigorous quality control, redundant sensor arrays, and cross-validation with multiple data sources are essential. Yet even after such meticulous filtering, certain signals persist stubbornly, defying categorization, remaining as unidentified or unexplained. These are the data points that linger in the scientific subconscious, quietly challenging the completeness of our understanding. The true enigma, however, lies in the unknown unknowns, the data that does not merely deviate from a known pattern, but that fits no existing category, no established model, no current hypothesis. These are the acoustic signals that bear no resemblance to any known marine creature or geological process. The chemical ratios that defy known biogeochemical cycles. The geological formations that cannot be explained by plate tectonics or erosion, or the energy fluxes that have no identifiable source. When such data emerges, it triggers a profound scientific perplexity. It forces researchers to question not just their interpretations, but the very foundational assumptions of their fields. Is our understanding of deep-sea biology too limited? Are our geological models incomplete? Are there fundamental physical processes at play in the deep ocean that we have yet to discover or fully parameterize? These are the moments when the data deluge, instead of clarifying, deepens the mystery, opening new frontiers of inquiry. Interpreting these truly unexplainable phenomena often demands an interdisciplinary approach, drawing upon the collective expertise of oceanographers, geophysicists, marine biologists, chemists, and even computer scientists. A cryptic acoustic signal might require a biologist to consider undiscovered species, a physicist to ponder unusual sound propagation, and a geologist to investigate deep-sea seismic activity. An anomalous chemical signature might lead a chemist to hypothesize novel reactions, a microbiologist to search for extreme extremophiles, and a geochronologist to consider ancient geological reservoirs. This collaborative effort, while immensely powerful, also introduces its own complexities as different scientific disciplines often speak different languages, employ different methodologies, and possess different conceptual frameworks. Bridging these disciplinary divides, fostering a shared understanding of the unexplainable, becomes a crucial yet challenging aspect of modern oceanography. The role of algorithms and artificial intelligence in this interpretative process is growing, offering both promise and limitations. Machine learning models can be trained on vast datasets of known phenomena, enabling them to quickly identify familiar patterns and flag deviations. They can detect subtle correlations that might escape the human eye or process data streams at speeds impossible for human analysts. Yet these algorithms are only as good as the data they are trained on, and they excel at recognizing known patterns. They struggle inherently with true novelty, with the genuinely unprecedented. An AI might flag an anomalous signal, but it cannot by itself formulate a new hypothesis about an unknown physical process or postulate the existence of an entirely new life form. That creative leap, that intuitive spark that connects disparate pieces of unexplained data into a coherent, albeit speculative narrative, still largely remains within the realm of human cognition. Indeed, the human element, the intuition, the experience, the subtle aha moment, remains profoundly important amidst the data deluge. It is often a seasoned researcher, having spent decades immersed in the nuances of oceanographic data, who recognizes a pattern as truly off, who senses a deeper mystery beyond the statistical anomaly. It is the willingness to embrace uncertainty, to not immediately dismiss data that contradicts established wisdom, and to pursue the faint, perplexing signals that truly drives discovery. Yet this human element also brings with it a certain scientific conservatism. The pressure to publish robust, verifiable results to withstand rigorous peer review often means that truly unexplainable data, lacking a clear hypothesis or definitive evidence, might be discussed quietly among colleagues, filed away for future investigation rather than being broadly disseminated. There is a natural reluctance to present findings that cannot be unequivocally explained lest they be dismissed as error or mere speculation. Thus, the unexplainable often accumulates slowly, like fine sediment on the abyssal floor, building up over years, sometimes decades, until a critical mass is reached. A single anomalous data point might be an outlier. A dozen such points from different regions and different instruments begin to hint at a pattern. It is in this slow, patient accumulation of contradictions that the seeds of paradigm shifts are sown. The anomalous element ratios, the cryptic acoustic signatures, the geometric patterns without precedent, each in isolation, might be a curiosity. But when viewed collectively, when they begin to form a subtle, interconnected web of unexplained phenomena, they collectively whisper of a deeper, more intricate reality beneath the waves, a reality that our current scientific frameworks are only beginning to grasp. The long-term implications of these unexplainable data are profound. They remind us of the immense humility required when confronting the scale and complexity of our planet's largest habitat. They suggest that our maps of the deep ocean, both physical and conceptual, are still largely incomplete, filled with vast, uncharted territories of knowledge. They compel us to continue pushing the boundaries of technology, to refine our models, and to foster a scientific culture that embraces the unknown, not as a void to be filled, but as a boundless frontier of discovery. The data deluge, therefore, is not just a challenge of processing numbers. It is a profound invitation to reimagine the ocean, to consider its hidden chemistries, its silent voices, and its enigmatic forms as a living, breathing testament to the endless possibilities that lie beneath the waves, waiting for us to truly comprehend their profound and unwritten stories. The ocean as a mirror to the unknown within. The ceaseless, overwhelming torrent of data flowing from the deepest, darkest corners of our planet's ocean often presents scientists with fragments of information that resist classification, whispers of phenomena that defy our current understanding. These unexplainable anomalies, these subtle contradictions, do not merely highlight the limits of our instruments or our models. They gently compel us to acknowledge a profound truth that the external world in its deepest mysteries often serves as a mirror to the unknown within ourselves, reflecting the vast, uncharted territories of the human mind. Just as the deep ocean hides its secrets beneath a shimmering surface, so too does our inner world contain abyssal depths, rich with unacknowledged processes and enigmatic formations. Consider the immense silent volume of the deep ocean stretching across 361 million square kilometers, its true three-dimensional immensity largely beyond our daily consciousness. This vastness finds a profound parallel in the human subconscious, an equally immense and largely unexplored realm that underlies our waking awareness. Psychologists from Carl Jung to Sigmund Freud and beyond have theorized about this inner ocean, a reservoir of primal urges, forgotten memories and archetypal patterns that subtly influence our thoughts, emotions, and behaviors. Like the ocean's depths, the subconscious is mostly dark, inaccessible to direct observation, yet its currents and pressures shape the very landscape of our conscious experience. We navigate its surface, the ego, but beneath lies a world whose true scale and complexity remain largely unknown, a personal abyss that whispers its own cryptic signals. The crushing pressure of the deep sea, an overwhelming force that reshapes the very properties of water, and the biology of its inhabitants finds its echo in the psychological pressures we experience. The weight of unacknowledged trauma, the burden of unspoken fears, or the relentless demand of societal expectations can create internal pressures that, though invisible, profoundly alter our inner landscape. Just as deep-sea organisms adapt with specialized proteins and flexible structures to survive the physical squeeze, so too does the human psyche develop complex defense mechanisms, coping strategies, and adaptive behaviors to manage its internal pressures. The anomalies in deep-sea physics, where water itself seems to bend under the colossal embrace of the deep, might be likened to those moments when our own emotional equilibrium seems to shift unexpectedly, revealing a vulnerability or a strength that defies our accustomed self-perception. The subtle, silent forces of internal pressure sculpt our inner world in ways we are only beginning to comprehend, much like the ocean's depths. The unclassifiable biota of the abyss, those creatures whose forms and metabolisms defy our known biological codes, find their analogy in the strange, often unsettling imagery that arises from our dreams. In the nocturnal theater of the mind, we encounter figures, landscapes, and narratives that are utterly alien yet intensely personal. These dream figures, sometimes monstrous, sometimes ethereal, are like the unclassifiable inhabitants of the deep, emerging from the subconscious with forms that do not fit the neat categories of our waking world. Psychologists often interpret these as manifestations of repressed desires, archetypal symbols, or fragmented memories, their metabolic mysteries reflecting the complex, often hidden processes of our inner workings. Just as deep-sea organisms thrive on chemosynthesis, converting unusual chemical gradients into life, so too do our dreams. Process raw, emotional data, converting the chemical imbalances of our waking life into symbolic narratives that seek resolution or understanding. The profound adaptability of deep-sea life to extreme conditions mirrors the resilience of the human psyche, capable of finding meaning and even growth in the darkest, most challenging internal environments. The anomalous element ratios and isotopic shifts, those subtle chemical fingerprints detected in the deep ocean that hint at unknown sources and complex interactions, resonate with the chemical landscape of our own emotions and thoughts. Our moods, our states of mind are profoundly influenced by neurochemical balances, by the subtle ebb and flow of neurotransmitters and hormones. An unexpected surge of anxiety, a prolonged period of inexplicable melancholy, or a sudden burst of creative insight can feel like an anomalous element ratio in our inner world, a shift in the expected chemical equilibrium that hints at deeper, perhaps unacknowledged processes at play. The isotopic shifts which trace an element's journey through time might be likened to the way our present emotional responses are subtly influenced by the isotopic memory of past experiences carrying the faint but indelible marks of earlier traumas or joys. The hidden chemistry of our internal landscape, like that of the deep ocean, operates with an intricate, often mysterious elegance, constantly shaping our subjective reality in ways we are only beginning to decipher. The unpredictable global circulation anomalies, those currents of contradiction that deviate from the expected flow of the ocean's vast circulatory system, find a direct parallel in the unpredictable currents of our thoughts and emotions. Just as deep-sea currents can suddenly decelerate or shift course without clear external drivers, so too can our minds experience unexpected surges of creativity, sudden waves of introspection, or inexplicable shifts in motivation. The rogue eddies of the deep, those powerful, persistent vortices that stir the abyssal waters in unpredictable ways, might be likened to the intense recurring thought patterns or emotional loops that can dominate our inner landscape, seemingly arising from nowhere and stubbornly resisting easy resolution. These unpredictable internal currents, though often challenging, are also sources of profound self-discovery, revealing hidden pathways of thought or unexpected depths of feeling that challenge the neat, linear narratives we construct about ourselves. They are the silent, internal forces that reshape our conscious experience, guiding us toward unseen internal landscapes. The enigmatic formations and geometries, those patterns without precedent etched into the deep seafloor. The perfectly straight lines, the precise circles, the colossal solitary pillars find their reflection in the symbolic landscapes and structures that populate our dreams and our deepest imaginations. In the dream state, we might encounter perfectly symmetrical labyrinths, towering impossible fortresses, or vast geometrically ordered cities that exist only within the mind. These patterns without precedent in our inner world are not random. They are often deeply symbolic, representing the hidden architecture of our psyche, the organizing principles of our unconscious mind. Psychologists like Jung spoke of archetypes, universal patterns of imagery and thought that manifest in dreams and myths across cultures, forming a kind of geometric order in the collective unconscious. Just as the deep sea formations challenge our understanding of natural geological forces, so too do these dream geometries challenge our understanding of the mind's capacity for complex, often profound, symbolic construction. They are the silent internal monuments to the hidden structures of our being. Finally, the deep-sea energy signatures, the unidentified thermal and electromagnetic fluxes that whisper of hidden power sources and processes in the abyss, resonate with the subtle, often inexplicable energies that course through our own bodies and minds. The feeling of a sudden, inexplicable surge of energy, a profound sense of intuition that guides a decision, or a quiet, persistent inner knowing that defies logical explanation, can be likened to these unseen, unquantifiable internal fluxes. While often dismissed by conventional science, many psychological and spiritual traditions acknowledge the existence of subtle energies within the human system, flows of vitality or awareness that are difficult to measure yet profoundly impactful. These internal energy signatures, whether they are the quiet hum of creative inspiration or the subtle warmth of emotional connection, suggest a deeper, more intricate energetic dynamism within us. Just as the deep ocean exhales its heat and permeates its magnetic field, so too does our inner world radiate its own subtle energies, influencing our perceptions and interactions in ways that are only beginning to be understood. The journey into the deep ocean, therefore, is not merely an external exploration of water and rock, but a profound metaphor for the journey into the self. The scientific humility required to confront the ocean's unexplainable mysteries is the same humility needed to explore the vast, often contradictory landscape of our own minds. Both demand patience, courage, and an acceptance that the most profound truths often lie hidden beneath layers of convention, waiting to be acknowledged. To dream of the deep, to contemplate its silent, immense presence, is to hold a mirror to the unknown, within inviting us to explore our own abyssal depths and to marvel at the boundless, enigmatic wonders that reside there. The ocean in its deepest, most mysterious reaches continues to reflect the profound, uncharted territories of our own consciousness, eternally whispering its silent, powerful stories. The ceaseless, overwhelming torrent of data flowing from the deepest, darkest corners of our planet's ocean often presents scientists with fragments of information that resist classification, whispers of phenomena that defy our current understanding. These unexplainable anomalies, these subtle contradictions, do not merely highlight the limits of our instruments or our models. They gently compel us to acknowledge a profound truth that the external world in its deepest mysteries often serves as a mirror to the unknown within ourselves, reflecting the vast, uncharted territories of the human mind. Just as the deep ocean hides its secrets beneath a shimmering surface, so too does our inner world contain abyssal depths rich with unacknowledged processes and enigmatic formations. Consider the immense silent volume of the deep ocean stretching across 361 million square kilometers, its true three-dimensional immensity largely beyond our daily consciousness. This vastness finds a profound parallel in the human subconscious, an equally immense and largely unexplored realm that underlies our waking awareness. Psychologists from Carl Jung to Sigmund Freud and beyond have theorized about this inner ocean, a reservoir of primal urges, forgotten memories and archetypal patterns that subtly influence our thoughts, emotions, and behaviors. Like the ocean's depths, the subconscious is mostly dark, inaccessible to direct observation, yet its currents and pressures shape the very landscape of our conscious experience. We navigate its surface, the ego, but beneath lies a world whose true scale and complexity remain largely unknown, a personal abyss that whispers its own cryptic signals. The crushing pressure of the deep sea, an overwhelming force that reshapes the very properties of water, and the biology of its inhabitants finds its echo in the psychological pressures we experience. The weight of unacknowledged trauma, the burden of unspoken fears, or the relentless demand of societal expectations can create internal pressures that, though invisible, profoundly alter our inner landscape. Just as deep-sea organisms adapt with specialized proteins and flexible structures to survive the physical squeeze, so too does the human psyche develop complex defense mechanisms, coping strategies, and adaptive behaviors to manage its internal pressures. The anomalies in deep-sea physics, where water itself seems to bend under the colossal embrace of the deep, might be likened to those moments when our own emotional equilibrium seems to shift, unexpectedly revealing a vulnerability or a strength that defies our accustomed self-perception. The subtle, silent forces of internal pressure sculpt our inner world in ways we are only beginning to comprehend, much like the ocean's depths. The unclassifiable biota of the abyss, those creatures whose forms and metabolisms defy our known biological codes, find their analogy in the strange, often unsettling imagery that arises from our dreams. In the nocturnal theatre of the mind, we encounter figures, landscapes, and narratives that are utterly alien, yet intensely personal. These dream figures, sometimes monstrous, sometimes ethereal, are like the unclassifiable inhabitants of the deep emerging from the subconscious, with forms that do not fit the neat categories of our waking world. Psychologists often interpret these as manifestations of repressed desires, archetypal symbols, or fragmented memories, their metabolic mysteries, reflecting the complex, often hidden processes of our inner workings. Just as deep-sea organisms thrive on chemosynthesis, converting unusual chemical gradients into life, so too do our dreams process raw emotional data, converting the chemical imbalances of our waking life into symbolic narratives that seek resolution or understanding. The profound adaptability of deep-sea life to extreme conditions mirrors the resilience of the human psyche, capable of finding meaning and even growth in the darkest, most challenging internal environments. The anomalous element ratios and isotopic shifts, those subtle chemical fingerprints detected in the deep ocean that hint at unknown sources and complex interactions, resonate with the chemical landscape of our own emotions and thoughts. Our moods, our states of mind are profoundly influenced by neurochemical balances, by the subtle ebb and flow of neurotransmitters and hormones. An unexpected surge of anxiety, a prolonged period of inexplicable melancholy, or a sudden burst of creative insight can feel like an anomalous element ratio in our inner world, a shift in the expected chemical equilibrium that hints at deeper, perhaps unacknowledged processes at play. The isotopic shifts which trace an element's journey through time might be likened to the way our present emotional responses are subtly influenced by the isotopic memory of past experiences, carrying the faint but indelible marks of earlier traumas or joys. The hidden chemistry of our internal landscape, like that of the deep ocean, operates with an intricate, often mysterious elegance, constantly shaping our subjective reality in ways we are only beginning to decipher. The unpredictable global circulation anomalies, those currents of contradiction that deviate from the expected flow of the ocean's vast circulatory system, find a direct parallel in the unpredictable currents of our thoughts and emotions. Just as deep-sea currents can suddenly decelerate or shift course without clear external drivers, so too can our minds experience unexpected surges of creativity, sudden waves of introspection, or inexplicable shifts in motivation. The rogue eddies of the deep, those powerful, persistent vortices that stir the abyssal waters in unpredictable ways, might be likened to the intense recurring thought patterns or emotional loops that can dominate our inner landscape, seemingly arising from nowhere and stubbornly resisting easy resolution. These unpredictable internal currents, though often challenging, are also sources of profound self-discovery, revealing hidden pathways of thought or unexpected depths of feeling that challenge the neat, linear narratives we construct about ourselves. They are the silent internal forces that reshape our conscious experience, guiding us toward unseen internal landscapes. The enigmatic formations and geometries, those patterns without precedent etched into the deep sea floor, the perfectly straight lines, the precise circles, the colossal solitary pillars find their reflection in the symbolic landscapes and structures that populate our dreams and our deepest imaginations. In the nocturnal theatre of the mind, we might encounter perfectly symmetrical labyrinths, towering impossible fortresses, or vast geometrically ordered cities that exist only within the mind. These patterns without precedent in our inner world are not random. They are often deeply symbolic, representing the hidden architecture of our psyche, the organizing principles of our unconscious mind. Psychologists like Jung spoke of archetypes, universal patterns of imagery and thought that manifest in dreams and myths across cultures, forming a kind of geometric order in the collective unconscious. Just as the deep sea formations challenge our understanding of natural geological forces, so too do these dream geometries challenge our understanding of the mind's capacity for complex, often profound symbolic construction. They are the silent internal monuments to the hidden structures of our being. Finally, the deep sea energy signatures, the unidentified thermal and electromagnetic fluxes that whisper of hidden power sources and processes in the abyss, resonate with the subtle, often inexplicable energies that course through our own bodies and minds. The feeling of a sudden, inexplicable surge of energy, a profound sense of intuition that guides a decision, or a quiet, persistent inner knowing that defies logical explanation, can be likened to these unseen, unquantifiable internal fluxes. While often dismissed by conventional science, many psychological and spiritual traditions acknowledge the existence of subtle energies within the human system, flows of vitality or awareness that are difficult to measure, yet profoundly impactful. These internal energy signatures, whether they are the quiet hum of creative inspiration or the subtle warmth of emotional connection, suggest a deeper, more intricate, energetic dynamism within us. Just as the deep ocean exhales its heat and permeates its magnetic field, so too does our inner world radiate its own subtle energies, influencing our perceptions and interactions in ways that are only beginning to be understood. The journey into the deep ocean, therefore, is not merely an external exploration of water and rock, but a profound metaphor for the journey into the self. The scientific humility required to confront the ocean's unexplainable mysteries is the same humility needed to explore the vast, often contradictory landscape of our own minds. Both demand patience, courage, and an acceptance that the most profound truths often lie hidden beneath layers of convention, waiting to be acknowledged. To dream of the deep, to contemplate its silent, immense presence, is to hold a mirror to the unknown, within inviting us to explore our own abyssal depths and to marvel at the boundless, enigmatic wonders that reside there. The ocean in its deepest, most mysterious reaches continues to reflect the profound, uncharted territories of our own consciousness, eternally whispering its silent, powerful stories, a ceaseless testament to the endless, unfolding mysteries that encompass both our world and our very being. And so as we drift away from the profound, silent mysteries of the deep ocean, allow the quiet contemplation of its uncharted depths to gently settle within your own mind. Just as the ocean holds secrets in its dark, unlit chasms, so too does your inner world prepare to unfurl its own enigmatic landscapes as you surrender to the embrace of sleep. Feel the gentle pull towards rest, knowing that the water flowing through your very being, a whisper of ancient seas, connects you to every silent current and every hidden abyss. The elements that compose you, the carbon and the oxygen and the subtle trace minerals, were all forged in the cosmic furnaces of distant stars, binding you to the vastness of the universe and the profound depths of our own blue planet. As your consciousness begins its slow, soft descent, let the immense, tranquil presence of the ocean cradle your thoughts, dissolving all waking concerns into the quietude of the deep. May the gentle, ancient waters guide your slumber. Sleep well, see you again.